What do you guys have for buffer capacity? Okay. You end up limiting, the buffer has a limit in the same way that, say, do you guys know what your bumper on your car, any car made like past 1990, is made of? It's nothing substantial. Seems pretty chintzy, actually. It's styrofoam. It's ultra high density styrofoam. Does that seem very useful? Well, what's a bumper for? Absorbing force. So what happens when your high density styrofoam runs into another car at 25 miles an hour? It crumples, absorbs that blow. Why are bumpers made 60 years ago really, really bad? They're made of metal. There's no give. You take all of the force. So now you get into a little fender bender and your bumper's destroyed, needs to be repaired. You have to take the front end or the back end off and replace all of that. So in that instant where your car runs into another car and your bumper gets destroyed, you've exceeded the buffering capacity of the styrofoam, and so you got to replace it. And so same situation here. I've reached the limit of what this thing can actually do. And what you end up doing is using up the weak acid or base. So one of those two things gets used up completely, with the base being the salt. Oops. Okay, so you're titrating an unknown weak acid with potassium hydroxide. You've got 35 milliliters acid in your amplifiers. Titrate 62 milliliters, 1.1. What's the concentration of your weak acid? So another just Na, Va equals Mb Vb. So your weak acid concentration, you don't know what that is. That's what you're looking for. Your volume is 35 milliliters. You have 1.1 molar KOH, and you added 62 milliliters to that. So the concentration of your weak acid is going to be 1.1 times 62 divided by 35. 1.9 molar. Okay, draw, label any titration curve. So let's go like this, and like this, like that. So volume of base, pH, it's the end point, point. Anything else you want to put in here? Not really. You could say the end point's the inflection point, but that's not a big deal. Oh, if it's you stated it was a strong base, then you'd want to put a 7 right there. But outside of that, nothing else. What would be the pH of adding 25 milliliters of 0.25 molar to 750 milliliters of pure water? So I need to know moles here. So I've got 2.5 moles per liter of KOH, and I have 0.025 liters. Liters cancel, and you end up with 0.0625 moles of KOH, and all I really care about is it's a strong base, and I've got 0.0625 moles of hydroxide. So then if I take the 0.0625 moles and divide it by 500, or actually just 0.5 liters, so we end up with 0.0625 divided by 0.5, and that's 1.25 molar hydroxide. So if I take the negative log of that, negative log answer close parentheses equals, I get 0.9, but that's my POH. So then that makes, if that's my POH, then my pH is going to be what? 13.1. Okay, yeah, super basic. All right, we're going to check what happens when we do that same thing, except this time to a buffered solution. So I had a pH change from 7 to 13, so that's 10,000 times, 100,000 times, 10,000 times more basic than it started with. What we need to do with this is figure out moles of everything. So we'll actually do this calculation first. So 3.14 equals 2.2, sorry, not equals, plus the log of 2.25 divided by 0.22, and this equals 4.19, a pH of 4.19. So we're buffering at 4.19. I want to know what happens when I add this base to it. It's going to go up, but how much is it going to go up? So I need to know moles. So I've got 2.25 moles of citrate per liter, and I've got 0.475 liters. And so that looks like it's equal to 1.069 moles of A negative. How come I'm writing A negative? It's just the anion, and I really don't want to write out the polyatomic ion formula for citrate. But I know what I'm looking at is some, in this case, sodium and the citrate on there, so I'm just going to have something that's negatively charged. That's the anion of a weak acid, and the weak acid is going to be citric acid. So this will be 0.22 moles of acid, weak acid per liter, and then I've got 0.475 liters, and so that ends up being 0.1045 moles of the acid. And I already have my value for the number of moles of, oh no, sorry, number of moles of OH. So then I'm going to write an ice table. Yeah, it's the one above, because it's the same stuff. I asked you what was going to happen if I put it in pure water, and now we're going to put it into a buffer. So we're still putting this same 0.625 moles of the KOH into the water. So I'll just use that. So acid, salt, ice. So this is going to be, how's that all messed up? How'd that thing get up there? 0.1045 mole HA. That's weird. Let's go over here. And so if this is 0.1045. This one's 1.069. Okay, so I'm putting in a base. What's the base going to react with? The acid or the base? Okay, so that means I'm going to lose this many moles, 0.0625 moles of my acid, but I'm going to gain exactly that much base because the acid's going to turn into the conjugate base. So add that to that, and then this ends up being 0.042. This one is 1.1315. And so then the pH is 3.14 plus the log of 0.1315, 0.042, and I guess it's 4.57. So the pH went from 4.19 to 4.57, which goes up, but it definitely doesn't go up as much as my my pure water, which went from 7 up to 13. Okay, so we got another buffer problem here. So I'm going to add, so we got lactic acid and lithium lactate. Wow, that's a lot of lithium lactate. I don't remember writing this one, but okay. So we've got, well, we might as well figure out what the pH is first. And then lactic acid, I'm going to look that up. Actually, I think I can just open this. Let's come all the way down to, so lactic acid's pKa is 3.08. So and this is 12.5 and 0.035. Just seems weird. But what's that work out to be? 3.08 plus log 12.5 divided by 0.035, close parentheses, equals. All right, so this thing's going to be buffering at a pH of 5.63. Ready? So we need to figure out moles of everything. And so the moles we've got, we'll start off with, let's just do the lithium first since it's here. So 2.5 moles per liter, and we put in 0.045 liters, and we've got, no, I was starting off with the lithium hydroxide, and then 0.035 moles per liter, and it looks like 0.75 liters, and then 12.5 moles per liter and 0.75 liters. All right, so 2.5 times 0.045 and 0.035 times 0.75 and 12.5 times 0.75. All right, so this one is 0.1125. Oh, I know why I did it now. And then this one is 0.02625. And this is OH. And this is the weak acid. And then this one is 9.375. There. Okay. So then I've got an ice table. Weak acid, conjugate base. And so this is 9.375, 0.02625. Okay, so I've got 0.1125 moles of OH. So what I'm going to do with it? Yeah, I'm going to end up subtracting off 0.1125, and then this is add 1125, and then this ends up being 0.1125 minus 0.02625. All right, so what ends up happening is this becomes negative 0.08625, which means I've got that much hydroxide left in the container. So what did we do? First question? I exceeded the buffering capacity of my buffer. So this thing isn't going to be buffered. So what happens is all of this weak acid gets used up with this. This much is left over of the hydroxide. So now I can do the same thing that I did earlier and take the remaining moles of hydroxide. So 0.0825 moles of hydroxide divided by the total volume, which in this case is now going to be 0.795 liters. So that'll be 0.0825 divided by 0.795. And so we end up with 0.066 moles per liter OH. So then if I take the negative log of that, clear negative log, that gives me a pOH of 1.18. So I have a pH of 12.7282. So did my buffer work? Nope. Got used up, and then the pH dramatically changed from this 5.6 up to 12.8. So even though it canceled out some of the base that went in, it didn't cancel out enough of it to keep the pH from changing.